So my name is Fred Keem. I am a product manager at HBM Software. I'm in charge of all the signal processing tools we have, and hence why I'm pushing for you guys to be aware of signal processing skills that you may need in order to do a good job in FE simulation. So. Prensia, who are we? I'll just start by introducing the company. So we are part of HBM, and we provide our customers with software for reliability, durability analysis. So here are the software we develop and put to the market and support, etc. So on the left-hand side here, you've got Weibel++, Alta, BlockSim, etc. Those are software for reliability analysis, for test planning and system modeling. In the column in the middle, you'll have tools for reliability management. So that means you want to manage risks, you want to manage your maintenance and actions that you want to take. And on the right-hand side, on the right column, you have all the nCode tools. So that's for durability analysis, whether we're talking FEA-based fatigue or measured data, test data analysis. We also have IPSys for acoustics and vibration analysis of measured signals. The last one is Akira, which is a web portal to access to the measured data and to access to the encode tools with secure access, etc. So in this presentation, we'll focus on a design life, so that's for the FEA-based fatigue analysis, GlyphWorks, general purpose test data analysis with quite a few options related to durability, and IPSys, so that's for acoustics and vibration, so we mention things like modal analysis, for instance. So let's start. So again, you're probably all very familiar with FEA, and as you understood, we are coming from the fatigue and durability world. So I'm gonna present here what we call the 5 tricks box, and it helps understanding what are the inputs to fatigue analysis, and typically you may wanna loop through that, maybe changing slightly the geometry or the loading environments or the material properties to maybe enhance your fatigue results. So basically, here we're going to concentrate on the loading environment in this presentation, and typically, you know, the fatigue being so sensitive to the range of stress response, the number of cycles of stress. You want to make sure that the loading that you use is representative of the real loading, right? And I'm going to insist on that during that presentation. So by representative, I mean you should be able to reproduce the real amplitudes. That's crucial for fatigue. But also you need to capture the number of occurrences. Those amplitudes happen in real life during the life profile of your components that you're designing. You need to capture sequence effects that can play a big role in fatigue. The phase between multiple inputs is important. It can be very important, you know, in phase, out of phase, or you know, you have to take this into account. And also the frequency content. So that's important. If you have resonance modes, you want to make sure that you consider any dynamic behavior. So if you're an nCode user, you're lucky because Design Life and GlyphWorks, and I should have written IPSys as well, they all share the same interface. This means that if you're running a Design Life job, so you're aiming for that type of display where you get a contour plot of damage or fatigue life, you may as well use real measured signals. There's nothing like using real data, right? And by doing so, you may need to do some digital signal processing. So You may want to calculate some spectra or histograms, and you may want, we'll see that in the next slides, you may want to correct for some anomalies and things like that. So that's a real advantage of ours. You've got both tools like the FEA fatigue side and the test data processing side of things within the same interface. So in terms of signals that we can use, as I said, typically there's nothing like using measured signals, and they typically provide from data acquisition systems such as our hardware, the HBM hardware, or SOMAT, which is part of HBM as well. But other hardwares, that produce file formats which we read natively. So we get like 20 or 30 different hardware that the file formats we support. Now, when you work with real data coming from the field, you're exposed to an awful lot of potential issues. Those of you who are familiar with data acquisition will know that it's never perfect. You get noise and all sorts of artifacts that can pollute the signal. So it's always a good idea to check the signal's quality. So in this example, we're running this automatic reports in GlyphWorks, where we look at the signal. We may want to zoom in, out, etc. We look at how the signal, the data is distributed in that signal. We may want to look at histograms, like transition histograms, rainflow type histograms, spectra to see what sort of frequency content is hidden or is in this signal, and also statistics here. So we'll see each and every one of those results in more details in the next slides. First of all, the signal that come from in-field data acquisition can be, as I said before, polluted with anomalies. And requires cleanup potentially. It happens, unfortunately, in a lot of cases. So when I use the word anomalies, I mean drifts, spikes, saturation, recalibration, during the tests, electrical interference, etc., etc. So in some cases, the signal is unusable totally, and therefore you have to redo your test. And in the software, we can characterize that, the quality of the signal. In some other cases, some anomalies can be cleaned up. So, for instance, a spike here can be replaced with a straight line, or a flat portion like that, like loss of signal, can be deleted very easily. So we got means to automatically do that, or let the user do manual actions on the signal. And we got a number of icons in the software. We call them glyphs. We've got a number of glyphs for addressing signals anomalies. The first, before going into more into the signal processing side of things, one very important topic to have in mind is the sample rate. Nowadays we're using digital signals, so what looks on the screen like a continuous signal is actually made of discrete data points, and you really have to be careful what sample rate was chosen, right? So if you happen to have a sample rate that's too low, so like 1 point per second, whereas the data is meant to represent some phenomenon occurring at 10 hertz typically, that's far too low, right? And the risk is to completely miss some frequencies and miss the amplitude of the signal. So we have the famous Nyquist criterion that we need to theoretically, that you want to follow, and this one says that you need to sample your signal at least twice the maximum frequency that you think the signal contains. So let's take an example here. Let's consider this 20 hertz sine wave represented in red, and we want to sample it at 35 points per second. That's the blue one. So we're below the Nyquist criterion. So we're below the 40 hertz, 40 points per second that the Nyquist criterion would require. And what we see in here is indeed what's called aliasing. So you're missing the peaks of the signal, and you're introducing frequency content that doesn't exist. But in simple words, you can't reconstruct the original signal based only on the blue data points, right? So you haven't sampled your signal high enough. So let's sample it at 100 points per second. So we are far beyond what's required by the Nyquist criterion. But still, what we realize is we may or we will miss the peaks and the troughs. So even being 2.5 times higher than what's required by the Nyquist criterion is not enough. So let's sample it even at a higher rate, like 200 hertz, 200 points per second. So that's 5 times the Nyquist criterion. Still, you might miss the exact peaks and troughs. And for those of you who are familiar with fatigue analysis, it's extremely important. It's fatigue again is very sensitive to the stress range or amplitude. And if you're missing the amplitude by 10%, well, you'll have a 50 or if not more 100% error on your fatigue results. So as a rule of thumb, it's typically recommended to sample at least 10 times the maximum frequency. So 20 hertz, at least 200 points per second. It's really a minimum required, because you see here it's still not exactly capturing the extrema. So that's valid. When we're talking data acquisition exercise. You get a signal from your test department. If it's meant to represent road load data, you'd expect like up to 30 hertz. So following that rules, you expect a signal that's sampled at least at 300 hertz. If it's not, and it's meant to represent road load data, chances are that you're going to miss some amplitudes. But it's also valid if in the software you're generating some signals. You want to generate some swept sign, for instance, to use in your fatigue calc. Well, look at the maximum frequency of your swept sign and make sure the sample rate you choose is, again, at least 10 times higher than this maximum frequency. So enough with sample rates. I think I got my message across, I hope. Now talking about frequency content, typically you may be interested in looking at the spectrum of your signal. So if you happen to get a loading signal from your test department, or do your acquisition yourself, you might as well build this very simple process in GlyphWorks, where you have the input signal, a frequency spectrum glyph, followed by an XY display displaying the spectrum or the spectra if you get many signals. And that's interesting mostly for two reasons. The first one is to see whether you get noise in your signal, so which you may want to correct by filtering. That's the next slide. Another reason, probably more important, is to assess whether your excitation signal is penetrating the territory of resonances, right? If it's likely to excite some modes, in that case, you may want to do a dynamic FE analysis. If not, you may just do it may be enough to do a quasi-static analysis. So let's have a look at the first scenario where you have noise, for instance. So noisy signals, that's everyday's life of the data acquisition specialist. So you may want to, as a post-acquisition task, you may want to filter that noise. So typically here in this case here, we've got the red signal, which is very noisy, and we did a low-pass filter to get hold of the central tendency of the signal. So removing all this high-frequency noise. And you can then compare the two spectra before and after, and you should see a clear cutoff at the cutoff frequency you chose in your filter, and below which there's no energy in the spectrum. So we get several filters, the most famous one being probably the Butterworth filter. It's a time domain filtering. It's using a time domain filtering algorithm, and this is recommended when you do a fatigue analysis, because it's really focusing on the signal, on the time waveform. The other filter we have is the fast Fourier filter. So basically, it creates an FFT of the signal, removes the frequency lines you don't want to see, and it does an inverse FFT. So this one is not focusing on the time domain, on the time waveform, the quality of the waveform. It's on rather concentrating on the frequency content, on the spectral aspects. So for the acousticians, the vibration guys tend to prefer the fast Fourier filter, whereas the fatigue experts typically want to use a Butterworth filter. But both, it's they provide very similar results, as a matter of fact. So that's for removing the noise. Now the other scenario why you wanted to look at the frequency content of an excitation signal is to observe whether the energy is below a fraction of the first natural frequency of your system. So typically, as a rule of thumb, we try to make sure that the excitation signal is below 1/3 of the first natural frequency in your component, in your device that you want to design. And if it's the case, if it's below 1/3, well, you might as well just do a quasi-static analysis and might just go for a linear static superposition. If not, then you'll have to take into account the dynamics, because the stress will be amplified due to the resonance effect. And the closer you'll be to the resonance, the more the stress response should be magnified or amplified, I should say. So in that case, you'll have to go for a dynamic analysis. So you can do that in the time domain. So you could go for direct transient analysis, but that'll be very demanding in terms of CPU time, etc. So if you're in the linear case but dynamic, you could go for model superposition and do your fatigue bit in design life, or you can work in the frequency domain if you are following a number of assumptions, including stationary excitation signals and Gaussian excitation signals. Then why not working with the PSD of the excitation signal? And you'll, in both cases, if this excitation, if the excitation signal is getting any closer to one of the modes, you'll see what we call mode shape, and you'll see very high stresses due to that mode shape, right, to that deformation due to the dynamics. So it's really important to make sure you take this into account and you do things such that they represent what happens in reality, and you don't miss this amplification of the stress. But I'm digressing here. Let's go back to the signal analysis. One thing you may want to do is characterize the statistical content in your signal. So you may want to do some histograms, such as the rain flow cycle count histogram, time at level, histogram level crossings, Markov or transition matrices, and all those results help us answer some questions like, is my signal Gaussian? So typically, if it's Gaussian, you expect this time at level or probability density function to show a bell-shaped to have a bell shape like that, right? Like a typical Gaussian distribution. Does it contain anomalies? Like if you have one, you may have in your rain flow cycle count histogram, that's a range mean. So this little cycle lost here at the very high range and will be by far the most damaging. So since it's far away from the distribution, is that a real data? Is it not an anomaly, a spike, for instance? So it helps identifying things like that. Along the same lines, you'd expect if your signal is meant to represent a rather long period of usage in real conditions, you'd expect a smooth histogram and not those holes, not those discrete towers here and there. You'd want something that's more smooth, and therefore it helps answering the question: have I covered a sufficiently long signal? You know, have I covered the statistical spread that may as well occur by taking a sufficiently long signal? Yes or no, right? So that helps you decide whether it's good to work with the signal or not. So this is to do with the classification algorithms. But from that distribution, typically the probability density function, we can extract some statistics. So the mean, for instance, that's a green vertical line that you can see. That's the mean of this distribution, the mean of the signal, but also the standard deviation. So how wide is this bell shape here, or the RMS, which is the same as standard deviation if the signal is centered around 0. So both mean and standard deviation characterize central tendency and spread of the data respectively. So that those are very interesting metrics. But we can go for higher order statistics. Typically the skewness will tell you about the symmetry of your data. Is it leaning more towards the negative values or the positive values? Typically a Gaussian signal will have a skewness of 0. But a more popular one is the kurtosis, which tells you about the impulsiveness of your data, or how many or how much do we spend at the extreme values typically, right? So the dashed black line here is a Gaussian curve with kurtosis of 3, and the red one is a very impulsive signal. It's coming from very impulsive signal. It's got a kurtosis of 9, so you can tell it's spending far more time at the very high or very low levels, right? So those are statistical metrics that you may want to use to characterize your data. So here we're talking of the use of DSP. So far, we saw how DSP can help you characterize your data, find anomalies, and address those, filter them out or clean up the signal. Here, another use of digital signal processing is to simplify your FE analysis. So in that case, we've got a non-linear, typically a non-linear model where compression and tension will produce different stress contours. So you've got two solutions there. By default, you'd want to do a non-linear FE analysis, but that's again complex and will be very, very demanding in terms of CPU time. The other solution here would be to separate your force signal, for instance, into two parts, the positive part, and which would represent the compression, for instance, in that case, and the negative part for the tension, for instance, and both will be associated with the stress contour due to the unitary compression or tension loads, and so that at each node of the signal, so we do a linear superposition, and at each node of the model, you'll have the contribution of both the tension and compression. So you're turning something that looks like a nonlinear case into a bilinear, if you like, case. So you do two linear analysis basically, and this all this involves is indeed to separate what's positive in your signal from what's negative. So that's a nice and interesting use of signal processing. I've got plenty of others. I thought of this one because it's quite common. Another is when you have many loads. If you do your mission profile for your components, you should have measured different situations, different users, different times in the day or in the year, or you get, or you know, or different locations, etc. So you may as well end up with hundreds of those loading signals, and you can't afford to run a fatigue analysis taking into account those hundreds of loading signals. So maybe you want to just limit your analysis to what's the most severe one, and therefore obtain some conservative results. So how to compare severity between different situations, or different locations, or different conditions in general. Well, one technique is to compute a relative damage by using a very simple fatigue analysis. You give it a fatigue slope of a pseudo ascent curve, and as well as comparing the standard deviation between two signals, you may as well compare the damage. So the damage becomes a metric, just like the other statistical scalar values, right? And helps defining which one is most severe. Another slightly more elaborate severity comparison uses the fatigue damage spectrum, whereby it's a similar thing. You know, you've got damage values, but per frequency. So you might see that some event is more damaging at high frequencies than at lower frequencies, and things like that. Very simple DSP, digital signal processing techniques, can help you choose what's the most severe loading out of a number of signals, and use this one for your FE analysis. Now, another case where you want to simplify your analysis because you get too much data, say, and you want to synthesize some vibration environment, say, or loading signal into something simpler. So maybe the simplistic way you may want to do is turn this complex signal into a constant amplitude signal, which has the same damage. So we've got a worked example in the software that helps you doing that. So you decide how many cycles you want, and it'll find the amplitude of that constant amplitude signal, such that it represents the same relative damage as this measured quantity here. So that's one way to go. Another way to go is to use the accelerated testing package we have in Vibesys and GlyphWorks, whereby you have you want to synthesize a vibration environment made of many different situations together with a number of repeats or occurrences, and you want to synthesize that into a PSD typically, or sign sweep, or sign on random that's equivalent in terms of damage. So this simple 5-6 breakpoints PSD has the same damage as so many times this situation plus so many times this situation. In other words, this PSD represents your life profile. It's got the same damage, and it's to be applied on your FE in your FE analysis for so many hours. So that's another way of synthesizing a complex set of measured data into a simplified specification for your analysis. So all this was purely so far acting on the inputs loads. Now there's something else that sometimes we do not have in mind, is the fact that indeed, if you are in the case where the FEA that you need to do is a dynamic analysis, you need to characterize your resonant modes. If you remember, I said that the closer you go to a resonant frequency, the more the stress response will be amplified. Well, this amplification coefficient is linked to the amount of damping that you have. And when you run a dynamic analysis, whether it's transient or a frequency domain, you always have to give your FE code a damping value, maybe a global damping value for all your mode, or you may as well give a damping value per mode. So this damping value, there's no other way than obtaining it via model tests. You need to test your structure by impacting with a hammer. That's the most common model test that we can find out there, or by exciting it with a shaker, either by a sine sweep or at a fixed sine or a random load. But you need basically some excitation signals, some responses, and you calculate. So in blue you've got the FRF, the frequency response function, and you can clearly see some peaks there. Those represent some modes. And what we do here, using the experimental model analysis glyph that we have in VibesYs, we will curve fit this measured FRF. And by doing so, we're fitting a theoretical model, and this enables us to extract sort of the natural frequencies, but also the damping ratios. So 3%, 4%, 1%. Each mode may as well have a different damping ratio, and that's typically used to enhance your FE modeling of the dynamic behavior of your components. So you've got a realistic loading signal that you're now using. You know it's clean. You know its frequency content. Maybe it's dynamic, so you've run a dynamic analysis. You made sure you've captured the right modes. They correspond with reality because you've done your model test, and you've captured the right damping ratio as well, so the right amplification that will be applied to the stress response. There is no harm, and it's strongly recommended to now correlate your stress results obtained from FE analysis with what you measured. So we have in Design Life this virtual strain gauge tool here, so you can position a or many strain gauges on top of your FE model. Then you load your FE model, and basically you extract the strain or the stress that goes through the strain gauge in that direction, right, in the direction of the strain gauge. The objective of that is to compare that with what you measured on a test rig typically. So the test rig, say you're using hydraulic actuators to load your specimen. The test rig will use the same signals as you used in Design Life for loading the physical components, and you capture the stress response. So if you're lucky enough to be in that situation where you can, in parallel, you run your FEA and you run your physical tests, then please make sure you've used strain gauges, so physical, metallic, or optical strain gauges in one case, and virtual strain gauges in the other case, and then that enables you to compare the extracted stresses. Again, typically, what's that for? Well, it enables you to verify that the way you've applied the loads, the way you've set up the boundary conditions was correct, right? Then you can verify that the material properties you've used for your FE analysis makes sense, is representative of the, and enables you to correctly model the real behavior. Also, a typical question is my mesh size sufficiently, sufficiently small? And sometimes you're running a quasi-static analysis and you wonder if the rule of thumb 1/3 of, you remember if you're below 1/3 of the first natural frequency, you find with a quasi-static, but sometimes you're like, oh, even though I'm a bit below 1/3, there's still some kind of little amplification of the stress, or there might be. So I may want to double check that I'm okay in terms of the stress levels. So for all those reasons, comparing the stress or strain obtained from a test and from FEA is useful. So here we're just simply overlaying the signals, but you could do you could cross-plot them and see whether all the data points follow on a diagonal line, more or less. You can calculate the correlation coefficient. There are plenty of analysis we could do to compare that and come up with one metric that tells us whether they fit or not. So I guess I've come to the almost last slide of this presentation. So that's a summary where we insist on the fact that the loading signals that you use should be representative, because again the fatigue results will be extremely sensitive to those, right? And measurements in service, in service data is the best thing you could probably have, because it's nothing like that in terms of representativity. However, make sure that the signal is clean, it's not polluted. So those in-service signals represent or capture real amplitudes, number of occurrences, sequence, phase relationships, frequency, content, etc., etc. Now, in this case, you want to use digital signal processing to check for anomalies again, observe frequency content, look at stats and distributions, and compare severities. But we saw that you can also use digital signal processing to reduce your measured signal into something easier, more compact, synthetic, and equivalent in terms of damage. You can use DSP to characterize the model properties of your structure and therefore enhance your FE modeling of the behavior of the component. And last but not least, you may want to use digital signal processing to correlate the strain response that you've calculated with the strain response that you've measured. And let me just finish off with this slide here. All I've been going through is actually, I haven't even invented anything. We've got a number of papers, articles around all those topics here, but if you are a user of the nCode software, just go in the help and you'll find worked examples. And we've got a number of worked examples showing you, illustrating all I talked about. So GlyphWorks worked examples, Design Life, Vibesys worked examples covering all we did, frequency content, spikes, removal, transient analysis versus model superposition in Design Life, equivalent constant amplitude signals from real measured signal that is ISO damage, synthesizing of a PSD, frequency domain fatigue analysis in Design Life, model analysis, experimental model analysis, right, and virtual strain gauge correlation. So I think I've reached the end of this presentation. I really hope you enjoyed it. I really hope you learned something, at least one thing you can take away, and I'm happy